Hello, let's talk about exponential functions today. First of all, before we discuss about the functions, we need to understand the general equations when it comes to exponential expressions. This is the most basic equation that you must remember. This tells you how much you will have when you, if I use money as an example, when you deposit, say, a principal of $100 for a certain number of years, say 3 years, at an interest rate of 10%. This formula will tell you exactly how much money you will receive with your interest, right, after the given number of years. So this formula is basically telling you the final amount after the given number of time with the annual rate of R. So here we go. P is the initial amount. It could be money. It can be on, like a value, right? It could be the number of people or anything. So the initial amount of something at an interest or any rate, right? So that's basically the percentage written in decimal, okay? So percent in decimal, or fraction, and T will be number of years. So once you plug in this information into this formula, you will then get A, which is the final amount. So let me give you an example. Say, since people do love money, let's do an example on money. Say you have $100 from your grandparents. Say 200 each, right? So you want to save this money up. So you look for a bank, and the bank offers 5% of an annual interest rate. Guys, having an annual interest rate is the crucial information that you must spot out, because say if the bank suggests 5% for any number of years, then you will have to use another formula actually to get how much money you will be receiving, as an interest, which is like something that we call as a simple interest formula. Most students do learn about simple interest in middle school or in elementary school. The formula says I equals to P RT. Ring any bell? Where I meant the interest, right? P, the initial amount, principal. R, rate in fraction or decimal, or T, the number of years. So if the rate is simply, the interest rate, right, for the entire, time that you put your money in, then you may just plug in the values into this simple interest formula to get your interest. However, if your rate, right, is gonna give you your interest at an annual rate, you must use this formula, because the difference between the two is that here you will first receive your 5% of interest at the end of the first year. So your 200 will increase, right? So when you get your second year's interest, you will be receiving 5% of the already increased amount. So technically, the increasing, the rate is keep piling up. Hence, the formula changes. You see the difference? So this is the initial amount, and this is the percentage. So let's keep that, in the bank for 3 years at an annual interest rate. So let's see. In order to see how much you will be receiving at the end of the year, you will have to just, plug in the values, 200, and multiply that by 1 plus 5% in decimal or in fraction, doesn't really matter, to the power of 3. And you will obviously need your calculator for this calculation, right? So whatever you get from here is the money in dollars, right, that you will be receiving plus, with your initially put deposit as well. So this is the growth formula. So what's a decay formula? Well, you see that teeny tiny negative sign underneath the, addition sign. Technically, right? If your value decreases annually by a certain percentage, 5% for 3 years, right? Instead of adding your rate from 1, you will have to simply subtract it, right? I mean, so we'll probably should use another example. So say you buy a car. You're too young to buy a car, but or maybe not. Okay, so say you bought a car and then you paid $500 for it. And usually cars do get cheaper as you keep it for longer, well, generally, right? So say the price of the car is keep dropping at 10% annual rate annually. And you want to see how much your car will cost in 2 years. So after 2 years, how much, money will will people pay for your car, basically? So it's going down. So before it was going up, but this time it is going down. It's decreasing at 10%, right, annually for 2 years. Hence, at the end of the 2 years, your car will be 500 times 1 minus 0.1 to the power of $9 only. So that's how we use this growth and decay formula. And most, it's really, very popular that they do use this interest-related questions with it, okay? Or, they can use something else. It's not always about the bank, right? So just to understand the meaning of this formula, and this formula can be used for interest questions as well as any value, as long as the value is being increased or even, being decreased by a certain percentage, annually. Okay? So that was the simple growth and decay formula. Let's talk about the second formula. The second formula, do you see how similar the two formulas are? Can you spot out the difference? Well, first of all, I didn't really put minus here because, this is usually, used for, interest problem, with of a bank. So this, for some of you, might already know the name of this formula. This is the compound interest formula. Do you remember compound interest formula? As you can see, the difference is that there is n divided by r and also multiplied by t. The p, r, and t are the same p, r, and t from the above. It's still p is still the principal, the initial amount. R, the percentage, the annual percentage, okay? And t is time in years usually. And a is still the final amount. So there's only one thing that we need to talk about. What is the meaning of n? What is n? As the name suggests, compound interest, n is the number of times, right, your interest being divided over a year. Like how many times it is compounded. And usually, always the question actually uses, the word compounded, right? So you don't have to worry about, understanding when to use this or not. They actually do say this is, compounded quarterly or for every 6 months or daily, right? Whenever that happens, all you have to do is just count how many times a year is being divided. If it says quarterly, that means it's being divided into 4, right? If it says daily, right, then it's 365. If it says monthly, then 12. Do you understand? So this is basically the number of times being compounded. Okay? So basically, just, you don't have to panic when it comes to compounding questions. All you have to do is memorize the formula and understand the difference between this formula and that formula. Again, it's not so hard. Just concentrate with the part where, if the problem says something about compounded, right? Use the second formula. If the question says simply something is being increased or decreased by a certain percentage annually, then use the first formula. Okay? So the first two represents the growth and decay with a percentage, annual percentage. Okay? So quickly, let me write the meaning of P, R, T, and N one more time. So the P, R, T, N for the first two formulas were, again, what was it? The initial amount, the principal, right? R, the annual rate, T, number of years, time in years, and N, number of times compounded. So if it says it's being compounded, say weekly, then what is your N? 52, right? Okay, now let's move on to the third formula. Ooh, what is that? It says P, well, same P, the initial amount, okay? And T, well, T must be the time. So what is N here? Well, actually, the N here is a bit different from the N up there. For this formula, let me just ask you some question. So say you have hamsters. You have like baby hamsters, right? Say there were 5 baby hamsters initially. And well, the number of hamsters were just keep increasing. It was doubling up, right? And then it takes, say, 5 minutes for the to double up its number. So you need to figure out the number of hamsters after half an hour, 30 minutes. Okay? So technically, the number of hamsters are being doubled up. And it's doubling, right? It's doubling for every, I say 5 minutes, right? For every 5 minutes. It takes 5 minutes for it to double up. And then you need to figure out how many hamsters there are after 30 minutes if you started off with 5. Okay, do you get the question? So basically, if you consider the situation, well, you understand the part that it's being doubled up, right? It takes 5 minutes for it to double up. So initially, well, there were 5, but 5 minutes later, you will be having 5 times 2, since, 10. Then, another 5 minutes later, you will be having 20, many of them. And do you see what's going on? Every single time, what you're doing is you're multiplying your initial value by 2 and by 2 twice, right? So for the next value, we already know that it will be equal to 40. However, if we write it, you keeping the 2 as 2, you see how we get 2 squared, and 2 cubed. It's being doubled up. So how many hamsters will we have in 30 minutes? And how do we actually get the value without having to continue writing out the numbers? Well, the formula helps us. The T over N here basically shows the number of times that the value P is going to be doubled up. If you think about it, it says 30 minutes, right? However, is the value gonna be good? Are you gonna double up the values basically 30 times then? No, it says 30 minutes. However, it takes 5 minutes for it to get doubled up, right? So technically what you're doing is you're doubling your value up by 2, right? How many times? Well, 6 times. You see? 5, 10, 15, 20, right? 25, then 30. So technically, what you're doing is you are multiplying your principal by 2 to the power of total time over how long it takes for it to get doubled up. So the number n, the letter n here basically represents the amount of time for it to get doubled up, so that the quotient tells us how many times it will be, doubled up. Can you understand that part? Just remember what n means. N is 5, right? Hence, t equals to 30. So we may continue this, sequence for the 30 minutes. However, if we just, choose to use the formula, right? Then we'll be doing principal 5 times 2 to the power of 30 over 5, which is 5 times 2 to the power of 6. Hence, well, that will be the answer to your problem, which is equal to 10 times 2 to the 5th, which is 4 versus 32, so 320 hamsters. Well, that's quite a lot of them, right? Okay, so well, these are the general expressions, formulas that you need to understand and memorize for exponential expressions. Well, the first one especially, you have to memorize. The latter two are usually given in the problem. However, the first one, you're supposed to remember it and use it from your memory. So please do make sure that you memorize the first formula. All right, now let's move on to the function part. So for any other functions, there were special things that you had to remember, right, and understand. For exponential, what you need to understand is that depending on what your base is, right, the shape of the graph will change. And it's an exponential function because your input here is actually the power, right? It's a to the power of x, and b represents like any coefficient to the power. So let's just consider having 1 as your b. So if your base a, right, is in between 0 and 1. Oh, by the way, guys, your base a can never be negative. Just remember that. So, well, for a reason, because if your base is negative, for even power, the outcome is positive, but for odd exponent, it will be negative. So it's going up and down. It's not exponential growth or decay. All right? Okay, anyway, so if your base is in between 0 and 1, so it's positive but less than 1 technically, right? You will get a graph, and if the base is greater than 1, then you will get a graph that looks like, well, this one, y and x, or f of x. So here we go. First of all, it will have, well, for any cases, you will have a y-intercept of 1, because no matter what your a is, a to the power of 0 is 1, right? Anything to the power of 0 equals to 1. So they will both pass through the 1, and they both have an asymptote. Remember what an asymptote is? Where the function approaches without ever intersecting it or touching it even. They both have horizontal asymptote at, well, y equals to 0. And like I said, it's exponential, so it should be growing or decaying exponentially. This one, for less than 1 positive base, it's actually decaying. So it's going closer and closer to the x-axis, but will never touch it. And for greater than 1, it will be growing then, decaying and growing. So depending on what your base is, you can already predict what kind of shape your graph is going to be. And exponential graphs are somewhat special because it's always increasing or always decreasing. It's kind of important that you remember that. Like this is kind of commonly used for SAT subject test, I think. Well, if you see a sentence that says, if x1 is greater than x2, then f of x1, say, is greater than or equal to or greater than f of x2. If you see a sentence right like this, what do you think this is actually saying? It says x1, x2 here, and it says f of x1 and f of x2 here. And everybody understands that f of something basically means the y value of that input value x, right? This is basically saying that the bigger the x, right? This is the bigger value, isn't it? The bigger the y. As x increases, right? The y increases as well. X increases to the right, right? Y increases upward. What does that mean? Your function will be going up as you go to the right. Hence, this basically means that your function is always increasing. So sometimes you're to find a function graph or a function equation that satisfies the following statement. That's the problem. Okay, so when you see a statement like this, you first have to understand that that they are actually asking about a function equation that is always increasing, and exponential do always increase, right? So you know, just remember that. That might save you some time when solving problems. And if I simply swap this part around, so if I go, if x1 is still greater than x2, then I'll swap the inequalities around for the function value part. If I say the bigger the x, basically the less the y, right? So technically, as x increases, your y will be decreasing. What does that mean? This means that your function is always, well, decreasing. It's always going down. So again, this will be the always decreasing function. So write down these two statements, and please do remember the meaning of each statement. Okay? All right, so again, remember what's so special about exponential function? You have asymptotes, and you know what asymptotes mean? Well, it means that your domain or range, right, might not be all real values. Well, for in this case, as you can see, the domain is all real values, right? So your domain is all real values. However, what is your range? The range is for greater than 0 values of y only, since 0 is the horizontal asymptote. So remember these details, and remember what happens to the direction of the graph depending on what the base is. Okay, so well, I'm trying to only go over the basics of exponential function because, well, honestly, for anything more complicated, you better just use your calculator. All right. Now, let's talk about properties. Well, this is something that you've been studying, well, starting from, say, Algebra 1 classes. So I'm pretty sure that you're familiar with the, well, power properties, right? So what are the basics? Well, first of all, for any of these properties, the bases were to be equal to each other, right? So we say if the two, so here we go, if you have equal bases, if they're being multiplied, the exponents are being added. If an equal base powers are divided, then you are subtracting, right? the exponents, if you have a power of a power, you're basically, well, multiplying out the two exponents, right? And if you have a negative power, it meant 1 over. Also, if you have a to the power of 0, that equals to 1. And if you have a to the 1 over n, that meant nth root of the base a. So, I mean, those are the properties of exponential, terms. Now, let's move on to another topic. Logarithmic properties, log. Why are we suddenly talking about log in the middle of exponential properties? Well, most importantly, it's because they are involved. This and this have a direct relationship between the two. Well, first of all, consider having a to the power of n equals to b. I may convert this into log with base a, b equals to n. You see what's going on? The base a goes as the base of the log, and the power exponent and the value, they swap, okay, around. You have to switch the positions, hence it becomes log. Exponential functions has an inverse, which is a logarithmic function, and vice versa. They are inverse of one another. So you need to understand logarithmic functions when you are studying for the exponential as well, because when we are studying for the exponential's inverse, we have to talk about logs. So that's why it's very important that you understand both and know the properties for both as well as the functions. Okay, anyways, so let's just continue. So first, for students who are not familiar with log at all, let me just quickly give you a quick lecture on logs. So log basically is like another way it's basically another way of showing the power and the value, but instead of like showing the exponents with the base, basically consider this, like you know that 2 to the something, right, equals to 8, right? So if you want to basically solve it for x, what you can do is you may just like change the format, right? We are not changing the number, we are just changing the format. Hence, we may just change the format and write 2, the base is still the base, and just put 8 next to the base, right? I said you swap these two around, the value goes next to the base, the exponent goes to the other side, hence then you may put x as the other side, and you just solve the x, solve for the x, I mean. So this is how exponential and logs are related, okay? It's just like another way of showing a power. Just think of it like that. It's really, really simple, actually. It's just that if you are not familiar with this, you might get confused at first because obviously you're seeing this for the first time. However, if you just like consider what I just said, it's just like it's like one more time. So if you have like 5 squared, and we know that this is equal to 25, right? This is boring, so I want to use log to rewrite this. So then I'll be writing log with base 5. 25 goes next to it, and that should equal 2. Again, same thing, but in a different format. Swap these around. Log has base, and we always write it as a small, writing underneath the, right next to the bottom part of the G, okay? And in a regular writing, we always write down what, the power is. So then you get a single value, hence that should equal to the exponent. The exponent goes there. The value, the entire value comes here. The base goes there. Exponent goes to the other side. Okay? Okay, so now if you understand what log is, let's just continue talking about the properties then. So before anything, you must understand how to convert one to another. Okay, so again, I'll just use ABC. If you have a to the power of b, that equals to c, you convert that into log. Base is the base, swap the rest of the values around. Okay, so this is like the how to convert. Okay, now properties are when you have log with some base a, and if you see that there are two values or a value and a variables or two variables, right, being multiplied, you may expand them out into two separate logs with the same base as a sum. Okay, second, similar, but this time, if they're divided, then you may expand this out as a difference. So far, so good. So if there are any two, right, a number and a variables, or two variables, right? If anything were to be multiplied within the parentheses, right, you may expand it out as a sum. This as a difference. And next, and this is really, really important, guys. And it's really, really simple. If your value has an exponent, well, for itself, then you may bring the exponent to the front as a coefficient to the log. Okay? Okay, next. If you see a value of a base, right? So same value. Then if you think about it, base to the power of something equals to the number itself. What must be the power? 1, right? A to the 1 equals to A. So it's kind of obvious. And if you see 1 as the value, what is the power? Well, obviously 0. Anything to the power of 0 equals to 1, right? Okay, and next. Well, this even has a name. Well, change of base property. Well, technically, base, right, is usually given. Say you have a log with base A with a value of b, right? You want to change that. You want to change this into something else. And hence, what you will do is you will just choose another base. Well, any base will do. Say any number, c, right? And put b on top and divide this whole thing by log with the same base c, the one that you just chose, with a. So what this is that the used to be base becomes the value in the denominator part, and you're using a new base c here for the quotient. When you do that, whatever this is still equals to what this is. So for this one, let me just give you a quick example. If you see log 2, 8, right? That is the same as log 5, 8 over log 2, 5, 2. Okay? So this and this should both equal to each other. You may use your calculator to prove it. By the way, if you're using TIs, right, especially TI 84s or TI 89s, well, when you go to math, if you have an old version of the calculator, you might not have it, but in math, there is a log base, button that you can use. You may actually type the base and the value, into your calculator. And for TI 89s, you have to go to log by pressing this, diamond and then 7. And then what you have to do is you have to put the value first, then the base. All right, you have to actually write the base after the comma. Just, remember that. All right, so change of base. We had just an example of that because this can be quite confusing, I think. It's quite complicated, isn't it? It's like creating something brand new. All right, now let's continue with other properties then. Other properties, well, actually, this is like more of a fact. Well, there are two special bases. One of them is base of 10. And the next one is a base of e. Well, they're special because when you have log with base 10, that just becomes log. Meaning, for base 10, you don't really have to write the base. And if you see your calculator, you will see a button that says log, right? That basically means that the base of this is 10. Okay? Now, for base e, you actually have to write ln. ln usually is right there in your calculator as well. ln means it is log with base e. So understand all these properties and please don't forget them because it's important not just for the math subject tests but for calculus and and further math as well. One last property though, if you have a base a and if the exponent itself is a log with the same base as before, it's really funny. They kind of cancel each other out and the only value that you have here is x. Okay, so I've given you some properties, right? And some facts that you must understand and remember. Write them down and memorize them. And if you're concerned about what e is, we just don't, you don't have to worry because e is just a number, like a pi, right? It's a number, but it's just, it's irrational. So they use e instead of writing out the number. Natural number, we call it. So if you're done writing it, let's move on to the last part of the class, logarithmic functions. So I don't know if you still remember what we just did in the previous page. We went over some exponential functions, right? You still remember the two different shapes? One's growing really fast, the second growing is decaying really fast, right? They both had horizontal asymptotes on the a-axis. Okay, so I said already that they are inverse, right, of exponential and vice versa. So let's just prove that. Here we go. If your f of x is equal to log of base 2x, right? How do you look for the inverse of that? Well, as always, you first swap the x and the y around. So you write this instead. And then what do we do? Uh-oh. If you don't know the simple properties, you'll be stuck, right? But since we do know, this will be so easy for us. Base is 2. The value over here is the exponent, remember? And this is what you will have to write over there. You see what's going on? You know what, we remember doing this, equals to c means that it's equal to log with base a, c equals to b. You see how we swapped these around when we were converting exponential into log? We are just doing it backward. You need to swap this back around so that this is the exponent and this is the other side. Okay? So this is our inverse for the given function. How's that? Quite simple, right? Well, if you're still not very confident about it, let me just do a quick another example. All right, so let's do something a little bit more complicated. say 1 minus log with base 3 x minus 1. Yeah. So we swap it. I'll use another pen, chalk. X equals to 1 minus log base 3 y minus 1, right? What should we do? What should we do? Well, we should get rid of the 1 first. So I'll be subtracting the 1. And since, you know, I want to get rid of the negative sign as well, so I'll just multiply everything by negative 1. Hence, right? This. Then, again, once you have your log, you know, on its own, all you have to do is just do swapping. Swap what? The base is the base. And the remaining two parts have to swap around. The one that is on the other side right now becomes the exponent, and the one that is with the base becomes the other side. Yeah? And finally, you add 1. Like that. That is how you look for the inverse of log function. Remember the swapping around part. Okay? All right, now. Shall we do an inverse example for exponential function then? Last question, really. So if the function is exponential, say 2x plus 1 minus 3, how do we look for the inverse of it? Swap it, swap it. X equals to 2, y plus 1 minus 3. And x, you add 3. Okay, so there's nothing more to add or subtract because your power is by itself now. So all you have to do is swap, swap, swap. Use log, base is the base. This and this, swap, swap them around. So you will be putting x plus 3 in here and y plus 1 here. Okay? And finally, x plus 3 will be subtracted by 1. Okay? And guys, don't forget, it's log of the entire x plus 3. You're never to expand this out. Don't even think about that. The only time where the expansion is allowed is when the two things are being multiplied. Remember the first property that we wrote down in the previous page? If you have 3 times x, then you may write log base to 3 plus log base to x, right? But having a sum of x and 3 means it's the sum of x and 3. Leave it. Okay? Now, this is the answer. However, since there were so many properties when it comes to log, if you are looking for another answer set than this, if you don't see this basically in the answer choice, then you must think about what kind of property can we apply here. Well, first of all, you see the 1. You may change the 1 into log as well. Remember that one thing? Remember how log base a was equal to 1? Remember that? Because a to the power of 1 is a, right? The thing is, and make sure that you use the same base as the other term. The thing is, if you write log base 2 x plus 3 minus log base 2 with 2, it still is the same equation. We're just using the property, right? And since, hey, remember the two, same base log subtracting meant what? Remember that part? The second property that we wrote down before? Having a subtraction with between the same two bases of logs basically meant having a quotient inside of a single log. This can turn into that. Isn't that interesting, guys? It's really interesting, right? So you may write this as an answer, but if you're looking for a multiple choice answer, and if you don't see this, then you may use a property, hence convert this into that. Okay? So please always remember the properties that you can use. Looking for the inverse of an exponential function or for the logarithmic functions are the two most important methods that you must remember, and you can't really do them unless you know the properties. So please do study the properties. And well, the function part, it's not that like insanely hard. It's actually quite simple because if we just go back to the exponential, remember this was the one that was decaying, and this was the one that was growing, and they both had y-intercept at 1, well, for coefficient of 1, right? So if this was the exponential, if you think about it, since this is the inverse of log, remember the relationship between the graphs of function and its inverse function? It had a special symmetry about y equals to x. Please memorize them. All right. So technically, excuse me, your 1, gets flipped over to here. Well, this one too. And you see how this is, this part, will be flipped up, behaving this way. And this part will be flipped over there, behaving this way. So it should be like that. Well, it's keep increasing, will increase forever. And this will be going towards to the y-axis without ever really touching it. Well, this too. If you're not very sure how to reflect because the shape seems to be a little bit more confusing, all you have to do is just reflect them portion by portion. So if this is being reflected, what would you get? Don't you get something like that? Don't you get that? And this part hence becomes like that. This is what you get. So again, the y-axis becomes the asymptote for this case. And if you consider the domain and the range of the exponential function before, do you still remember the domain and the range? Remember how it was all real values for the domain, but the range was greater than 0? The domain and the range swaps around for the logarithmic function. So for exponential and for log, for domain and for the range, it's all real values and y equals to greater than 0. For this, the domain is x is greater than 0 and the range is all real values. Okay, I'm just talking about a very simple log with some base greater than 0, with an x. So when transformations, so basically when things are added, subtracted, multiplied, or divided to f of x, the domain and the range will change, of course. Just check your calculator for the changes, all right? And least, but then the things that you must remember is the general domain and the range, Just always have this thought in your, head that the domain, the domain for log has to be greater than 0. Basically, when you have log with base 3 and x, it is not okay to plug in anything negative as x. All right? Your x cannot be negative. Remember that. It's really important because sometimes you might have to solve for your value for x, And then the thing is, when you're solving for the x with logarithmic, expression, sometimes, the things becomes a quadratic function equation. Do you remember the lecture on radical functions? How we were solving for a radical expression and it became quadratic. Hence, we had to plug in the values back into the original function equation to see, original expression to see whether the given value is indeed correct or not. Same thing is required for log. Well, the thing is, you may solve for a log expression by you know, making that into a power form. Or, well, there are many other things that you can do. However, I'm not going to go over this right now because this is actually outside of the math, you know, level 2 exam or level 1, obviously. So for these kind of questions, if you ever see a problem on your test where you have to solve for the x for log function or logarithmic expression, right? I just need you to, well, simply graph them. So for example, if you see, it's really, I think this is a kind of popular, like say, if the question asks about the value for x, right, where e to the x equals to negative ln of the x, all you have to do is just graph e to the x and graph negative ln of the x, right, from your calculator, and just find out where they intersect. Wherever they intersect, the intersection is the answer because they're equal to each other. So you don't really have to solve when it comes to log or exponential related expressions. You know, you don't have to solve it for the x by hand. And just, you know, just if you have a TI 89 or Inspired, then they will do it for you. If you have a TI 84, then you may graph them and look for the intersection. You know, it saves you some time and it's faster. I mean, that's, you know, good enough reason for why you should just graph it. So anyways, so there are a few things that you need to understand when it comes to log and exponential functions. And like I said, the functions are not as important as knowing the properties. So please, and again, the inverse, right? Looking for the inverse is like really, really important. So please practice on that. Okay, so thank you for listening, and I'll see you again with another function class.